Hello, good day everyone. As I have promised, we're going to have a video lecture on population size estimation. Now, as a start, I want us to recap the tips that I gave you in class about how to approach problems on population size estimation. So we have these 5 tips. The first thing that you need to do is to identify what you are looking for. So that means you need to look whether you're finding a future population size, whether you're estimating a past population size, or you are actually estimating a rate of change. So you need to identify which of those three are you actually looking for. Second is for you to compute the elapsed time between the two dates. Now, why is this a second step? In all of the formulae that you have for population size estimation, you will always be dealing with time. So might as well do it first. So in order to compute for the elapsed time properly, you should do future date minus past date always. So even if you're, let's say for example, you're estimating for a past population size, the way that you compute for the elapsed time would still be future minus the past date. And then don't forget the table that I taught you. Use that whenever you compute for elapsed time between two dates. We'll see the table again later in the more specific examples. The third tip that I want you to remember is to identify the other components of your formula through the given. So whenever you're given a case, you're always given the data for time, of course, which is given by the two dates. The next thing that you need to do is to identify the other components of the formula aside from the elapsed time, of course. So that would either be population size in the future, population size in the past, or the rate of change. After you have identified the other components of your formula through the given, the next thing that you would do, of course, would be to substitute the values of these different factors into your formula. Okay, now let's say that you have already arrived with an answer by substituting the values inside your formula. The next thing that you do is, first, if you're looking for a population size, which is either a future or past population size, you need to round up the final answer if it has decimals. So remember, rounding up is different from the concept of rounding off. When we round off, if it is 5 or greater, the decimal place, we round it up to the next whole number. But in rounding up, it doesn't matter how big or small the decimal place is. As long as there is a decimal place, you should round it up to the nearest whole number. And we already know the reason for this. Whenever we're dealing with population size, you know that we're dealing with people. So it would make sense if we would be having a measure such as 1,000,000.5 persons as the population size. Okay, now, what if you're looking for a rate of change? If you're looking for a rate of change, you should multiply your answer by 100 to express it as a percentage. Always remember this. Okay, now that we have gone through these tips, we'll now go into the exercises that I gave you. So just to recap, we have a table that contains population counts. So these are just population sizes for years 2000, 2010, and 2015 in the Philippines. And we also have rates of growth between 2000 to 2010, 2010 to 2015, and 2000 to 2015. If you would think about it, having all this given, we would have data for almost all of the factors that we're going to look for. Anyway, the reason why I wanted to give this exercise is to show you how different or how close would the answers be if you would be using the same set of information. For example, let's say that given the data on May 1, 2000 and given the data on May 1, 2010, what if I asked you to compute for the annual rate of growth between those two elapsed dates? Would it be close to 1.90 as shown here in the table, or would it be a little bit different? So I'm going to give a spoiler. Of course, we expect it to be somehow very near 1.90 because we're actually kind of using the same formula. All right. I would just like to remind everyone that we won't be dealing with the arithmetic method and the geometric method anymore. So all of the formulae that you should be remembering by now would be formulae related to exponential methods. Anyway, here are your tasks for these exercises. So first, we have to estimate the rate of change from May 1, 2000 to May 1, 2010. Let's go through them one by one. So the population size, we need to estimate the rate of change from May 1, 2000 to May 1, 2010. So let's go through the tips that I gave you. The first thing that we need to do, again, is to actually look to find what we're looking for. Okay. So what I'm looking for based on this is the rate of change. So what do you do when you already found what you're looking for? You write the formula of that thing that you're looking for. And the formula for rate of change would be the natural logarithm of the quotient of future population size divided by past population size. And then all of that divided by time. Okay. I hope you have written that already as you're watching this video. It would also help if you would perform or solve the problem as you go through the video. So I hope that you've already written the formula. The next thing that we do is, of course, to compute for the elapsed time. Now, in this example, it's very easy because we have May 1, 2010 and May 1, 2000. So we do know that the future time is May 1, 2010 and the past date is May 1, 2000. Now, the reason why I'm telling you that this is very easy is because in this example, we have the same months and day. So we have both May and both day 1. So for those components, if you'd be using this table that you see in the PowerPoint, you would have 0 for both month and day, and you'd only have a certain digit for year, and it is actually 10. So t here is equal to 10. All right. So what happens after we have computed for the elapsed time? The next thing that we do is to identify the other components of our formula. And here, the other components that we would be finding would be future population size, past population size. Is there anything else? There's none. That's all that you need to look for, future and past population sizes. Now, being able to look for that would enable you to actually get the natural logarithm of their quotients. So where do you actually find the values of these other factors? You find them in the given. So let me just browse back a bit in the table. We're looking for May 1, 2000 and May 1, 2010. So that would be for May 1, 2000, 76,506,928. And for May 1, 2010, we have 92,337,852. Okay. The next thing that we do after we have known what we're looking for is, of course, to substitute them inside our formula. So if you actually did it correctly, you should be able to arrive with 0.0188. Now, remember the last tip that I gave you. If you're looking for a rate of change, you shouldn't be leaving it just like this whenever you present it. We want our answers, especially those in decimal forms, to be expressed in percentages because percentages are more tangible. So we multiply this certain 0.0188 by 100 just to make it a percentage. So now we know that the annual rate of growth from May 1, 2000 to May 1, 2010 is 1.88%. Now, let's try to take a quick look about on how this compares with the annual rate of growth from from what is given from. So we have 2000 to 2010 1.90, and our computed one is 1.88%. That's actually somehow very close to one another. You see, the formula that we use is reliable. Okay. Let's now go to the second exercise. So we are asked to predict May 1, 2000 population size if May 1, 2010 population is 92,337,852 and that there was a hypothesized annual rate of growth of 1.90. Now, if you would notice, the dates that have been given in this second exercise are the same dates that we have for the first exercise. It's just that here, we're looking for a different thing. What are we actually looking for in this problem? We're looking for May 1, 2000 population size, and May 1, 2000 is a more past date than May 1, 2010. So you do know that what you're actually looking for in this exercise, in this problem, is past population size. We're estimating for the past population size. Okay, so now that we know that we're estimating for the past population size, of course, the next step would be for us to write the formula of what we're looking for. And the formula for what we're looking for is past population size is equal to future population size divided by the quantity E raised to the RT. Alright, I hope you have already written that. Next step would of course be to compute for the elapsed time. So again, we don't have any problems here. And take note, even though we are estimating the past population size, the way that we compute for the elapsed time is still future minus past date. And since we're using the same set of dates in this, with that of the first problem, our t is still equal to 10 years. Okay, so what's the next step? If computed for the time, the next thing that we do is to look for the other components of our formulae. So we already know time. What's left to know is future population size and annual rate of growth. Now, future population size would be, of course, 92,337,852, while annual rate of growth would be 1.90. Now, just a reminder, the usual way that annual rate of growth is given is through it being expressed already in percentage. So for example, in this problem, the hypothesized annual rate of growth is 1.90. That's actually a percentage. Whenever you use annual rate of growth in a formula, you need to first divide it by 100 so that you make it not a percentage, but rather in decimals. So whenever you're using annual rate of growth, make sure that it is in decimal form. So for example, 1.90, you divide that by 100, so you get to use an annual rate of growth of 0.019. All right. So now we know the components. We know the other factors of our formula. The next thing that we do, of course, is to substitute the values of these components. If you did this correctly, you should be able to arrive with 76,359,630.1. And if we are to do this, as you would remember in the last tip that I gave you, if you're looking for a population size and it has decimal places, what you should do is to round it up to the nearest whole number. And that is what happened here, as you can see. The answer, instead of being 76,359,630.1, the answer is 76,359,631. Okay, let's try to compare this with the data in the table. 76,359,631 versus 76,506,928. So we are still getting relatively close estimates, which makes us think that, okay, the formula that we are using is indeed reliable. Okay, let's have the third one. So we've already done an exercise that asks us to estimate the annual rate of growth. We have gone through an exercise that asks us to estimate the past population size. Now here, we are asked to predict a future population size. I have already spoiled you. We are to predict the population size for August 11, 2017. If the August 1, 2015 size was 100,981,437. Now, assume that the annual rate of growth is 1.50. Okay, what we're looking for is a future population size. And the formula for future population size is past population size multiplied by the quantity E raised to the R T. I hope you've written that already. Next step would be, of course, to compute for the elapsed time in years. Now here, it's also quite easy because all of the digits, all of the figures in future population size is actually larger than the figures in the past population size. For example, for day, future population size day is 11, past population size day is 1. For month, they're both 8. So there's no borrowing needed. For year, it's 2017 versus 2015. So you will not be practicing, of course, the concept of borrowing. Anyway, if you have done this correctly, your day should yield 10, your month should yield 0, and your year should yield 2. Now, of course, this wouldn't be our final answer. We want to express our elapsed time in years. This is what usually happens in population size estimation. We want to express time in years. But you could actually express your time in other variants, let's say, for example, months, or even in minutes, if we're talking about microorganisms. Anyway, we need to express this in years. So the way to do that is to actually add up the results for each of the columns. So for year, you have 2 plus the result in month, which is 0 over 12, which is basically 0, plus our answer for day, which is 10 over 365. So that's 10 plus 10 over 365, and that would give you a time equal to 2.027. Okay. Now, I arbitrarily rounded it up to 3 decimal places, but you can actually make use of a fraction instead. Or what I mean is that you may choose not to cut it off to certain or round it off into certain decimal places. What you can do in your calculator is that you store your answer. So let's say you inputted 2 plus 10 over 365. Let me show you. So I'm going to give you a hands-on here. So what we're going to do is 2 plus, what was it again? 2 plus 10 over 365. 2 plus 10 divided by 365, right? This should be it. There. Now, what I did was to cut it off into 3 decimal places, right? But you could actually just store your answer and input it directly to the formula. Now, what would be the benefit of just storing it and just using the ANDS function right over here? Of course, if you would be using the ANDS function, you would get a more accurate estimate of what you're looking for because you used all the place values of your time. If you cut it off to 3 decimal places, the accuracy might get hurt a bit. Okay. For the purposes of this lecture, I actually rounded it off to 3 decimal places. In the exams and exercises, we will be giving you specific instructions on what to do. But for now, what I want you to practice as a convention is to store your answer. That means just use the ANDS function in the future if you're going to use time in the formula. Okay, I would be showing that as well as we go through the PowerPoint. Okay, we have computed for the elapsed time. The next thing that we need to do is to identify the other components of our formula. So what are these other components that we're looking for? That would be past population size and annual rate of growth. Okay, past population size would be, of course, 100,981,437. And then annual rate of growth would be 1.50 as given. Now, okay, so I'll be showing you how you would be using the ANDS function in your calculators in order to save up all of the information that is within time. Okay, So you do that by, our formula is past population size multiplied by e raised to the RT, right? So let's do that here. You have past population size, which is, okay, 100,981,437 multiplied by its e raised to the RT. So e, and then r would be 1.50. Now, what did I tell you? Always use your annual rate of growth in decimal form. So that would be 0.015 multiplied by time. So the way to do that without wasting information would be to do it like this. Oops, pardon. There was something wrong with what I did. Okay, let's do that again. That would be 100,981,437 multiplied by e. That'd be raised to. You see that the previous mistake that I did is that I multiplied e to r and t. But what you should do instead is e and then multiply it by r, which is your annual rate of growth. Okay. Okay. Let's do that again. Pardon, I'm not very familiar with the Google Scientific Calculator. Okay. E raised to the quantity 0.015 multiplied by your time component, which is basically 2 plus 10 over 365. And then 2 parentheses. So this should give you a very accurate answer, which is, of course, a bit different with what you see in the PowerPoint. So which one is more accurate than the other? Of course, this one is more, the one that you're seeing in this Google calculator is more accurate than this one. Because this one used up all the information for time, while this one used time in with three decimal places. Now here, our final answer would of course be 104,099,552, because we always need to round up whenever we're looking for a future population size. Okay. I hope that you actually tried to solve this on your own so that you won't be having any problems in your exercises, in your graded exercises, and in your exam. Okay. Let's go back to the PowerPoint. Okay, we have one final exercise. It's just actually a bonus. But in this problem, it actually allows you to compute for the elapsed time, but certain figures for the past population size are larger than those in the future population size, as you would see later. Okay, we are to predict still August 11, 2017 population if the September 20, 2015 size was 100,981,437, and then we still assume an annual rate of growth of 1.50. If you'd be thinking about it, this problem has the same set of given from the previous ones. So this was just actually made for you to practice to compute for the elapsed time with a little bit more difficulty. Okay, so we identify what we're looking for. We're looking for a future population size. So the formula for future population size would be initial population size multiplied by e raised to the RT. Right. Hope you have written that already. Next step would be to compute for the elapsed time. Now, that would be future minus past date, of course. So if you would be creating the table, you would notice that the day for the past population size as well as the month are actually larger, and that is going to present a little bit more difficulty. So what we do here, let's say for example in the case of days, is we borrow from the months. We borrow 1 month from the month in the future. So if you're to borrow 1 month and transfer it to days, that would mean that we are to add 30. Okay. Not all months have 30 days, and there even you could actually still consider leap years if you would want to, but let's just make it very simple. Whenever we are borrowing months and transferring it to days, that would be a plus 30 in days. Okay. So 11 plus 30, that would be 41 minus 20, and that would yield 21. Okay. Now, for months, we borrowed 1 from it, so we currently have 7. So you should be looking at 8 minus 1 versus 9. And of course, 9 is larger, so we need to borrow 1 from the year. So borrow 1 from 2017 and transfer it to months. That would of course be 12 months. I hope you have no arguments regarding this. We have 12 months in a year. So 8 minus 1 plus 12, which is 7 plus 12, that would be 19. So 19 minus 9 would yield 10. And for the year, we have 2017 minus 1. That's 2016 minus 2015. That would yield 1. Okay, we know that these are not yet our final answers, so we should be adding them up for us to be able to express them in years. So we do 1 plus 10 over 12 plus 21 over 365. Okay, let me do that in your calculator. 1 plus 10 over 12 plus 21 over 365. And that would give us 1.890867, so on and so forth. In the PowerPoint, if you would be looking at the PowerPoint, sorry, here is what I did in the Google calculator. 1 plus 10 divided by 12 plus 21 over 365, and this yields this number here. What I did in the PowerPoint is that I rounded it off into 3 decimal places. So again, what I want you to practice is to actually make use of all the decimal places. I mean, you would be able to do that in the calculator by using the ANS function. I would be showing that to you. Okay, first, let's do the next step, which is identifying other components of our formula. Other components of our formula would, of course, be past population size and annual rate of growth. Past population size would be 100,181,437, and annual rate of growth would be 1.5. Okay, next step would be to substitute these values into our formula. And we'll go back to our calculator. Okay. So in order to make use of the ANS function, we're going to do 100,981,437 multiplied by E raised to R, which is 0.015, since we need to express annual rate of growth in decimal form, multiplied by time, which is our previously set answer. So you just make use of the ANS function. And that way, you'd be able to arrive with an answer that is near what you see in the PowerPoint. Now, between the two, of course, this one is a more accurate estimate than what you see in the PowerPoint. And again, the reason for that is here, in what I did in the Google Scientific Calculator, it made use of all the information that is contained within our computation of time. Here, this is an estimate that made use of only up to 3 decimal places of time. Okay. So our final answer, if you'd be considering all our data points, would be 103,886,580 because we would be rounding up. Remember the last step. If you're looking for a population size, you always round it up. Okay. So I hope that somehow solving demography problems became easier upon watching this video. If you have any questions, if you have any concerns regarding the lectures that I gave you, please do not hesitate to send me an email or to approach me. Thank you very much and hope to see you in class very soon. Good luck.